We're going to start with something cool, totally not related to the lecture. This is from the inside of an airplane from my skydiving course. You should be seeing me soon. I am being tested here for skydiving license. That's not me.
With this shirt?
Sorry?
With this shirt?
With this shirt, yes. I have a skydiving suit with a Superman logo. Very cool. This is me. And the instructor has a camera on his head. And I'm supposed to catch him. Yeah. So naturally, I got off on the wrong side and I wasn't so stable. Now I'm accelerating forward to get close to him, checking altitude, very important. And I'm trying to get closer, again checking altitude, touching base lightly instead of crashing, 360. Checking altitude again, another flip for fun. And now I'm flying aggressively. Notice the helmet. Big bada boom. And now the instructor is expecting me to open the chute. For some reason, I failed to do that. The instructor opened his chute. This is the moment I failed the exam. And you can see me opening the chute a lot later and on a very dangerous altitude. And that's about it. The purpose of this movie is just to get you really excited about this lecture. That's it. I'm not that good at skydiving. I just really like it. So it's a nice way to start a lecture and everybody remember me because it's a cool thing to start with. So, welcome. My name is Omid Vadati. I work at Investing. Thank you for investing for hosting us. Thank you for Guy for hosting us in his meetup. This is a course meetup session. And I'm going to talk about his Guy's meetup. Here's my meetup. I'm organizing Big Data Demystified. The theme lecture is this. I started this lecture about 2 years ago. I was VP engineering in Walla News. And I was supposed to build a big data platform which was scalable to ingest massive amounts of data. It was an interesting project. And there were a lot of challenges around it. So the first thing that was, Walla was not on the cloud at the time. And the second thing was the use case. We'll talk about them. So I had to find something which is kind of confusing because the business was not set yet. I mean, there was no clear product definition, clear roadmap to what we are going to do. It was clear, though, that we are going to create a company which is data-driven, and we're going to collect massive amounts of data from various sources. We'll discuss them in a bit. It's going to be fun. Based on this one-liner, I got the job. I mean, I asked for the job. I really wanted to do it. So let's go. I'm not the very best architect of big data, but I really, really like what I do. So take that as a disclaimer. But it doesn't mean you're not supposed to ask me questions. Ask me questions. This lecture is about 90 minutes, 90. So I have about 90 slides. So every 1 minute you will see a different slide. So try to keep up. If it's too fast, raise your hands, talk to me. It's a conversation. I'm not trying to puke data or architecture. I'm trying to share with you my experience. So a long time ago, we were very happy. Everything was simple in terms of architecture. There was a web server, an API, and a database for LTP, and a database for OLAP, and everybody was happy. Then came big data, and everything exploded and stopped working. Then came the cloud, and swooped us off our feet. And then came the invoice. which is a big problem in terms of big data because the invoice could be quite big. It didn't stop though. It kept growing. There were many platforms, many solutions, open source, vendor-based, paid, non-paid, cloud, data center. Even this landscape picture is a bit old and not detailed enough. So this lecture is about AWS mostly. I'm not going to talk a lot about data center. I want you to see the ecosystem, the landscape, and get a sense of what AWS marketing is doing wrong. I say wrong because they don't show it like this or like this. They show it like this, which they hide all the cool stuff, the open source projects, behind a big logo called EMR. We'll discuss them. I'm not sure why this happens. I'm really sorry. Okay, so the first thing we're going to do is cover some jargon, some architecture consideration and challenges. So jargon, I made an article in my website detailing some answers, but we'll discuss them here. Big data, from my perspective, there's a lot of definitions out there, but from my perspective, big data is when your infrastructure is unable to process the amount of data you have coming in, and naturally for analytics. Scale up or scale out is an architectural practice that basically states can you hear me? Okay. States the following. If my data grows, I just add more machines. That's scale out. If I have a problem with my data and I'm unable to process it, I maybe want to take a scale up approach, meaning take the machine and make it larger with more CPUs and more RAM. Structured, semi-structured, and unstructured. Put it simply, CSV, JSON, JPEG, in that order. Structured, where you have a schema, a table-like with columns. Semi-structured, there's no false schema, so you can manipulate the data and not break anything. And unstructured is binary stuff, like movies and so on. ACID is not so important for the conversation so much, but I want you to remember this jargon, because in big data you don't use ACID solutions mostly. So it's one of the big differences between OLTP and OLAP. But I want you to not think of it in terms of ACID, I want you to think of it in terms of analytics versus of operational. Meaning there are two types of data infrastructures. Those who handle production applications, for example, login, and those who handle questions like, who is my user, what does he like, what has he been doing in my website for the last year and so. DIY, meaning do it yourself. PaaS, platform as a service. Okay, so we talked about the big data and what it means to me, but there are some definitions which are good and useful. For example, the 4 V's, volume, velocity, variety, and veracity. Volume is how much data you have, velocity is how much data coming in terms of gigabyte per second, the variety is the types of data you are getting, the veracity, how much is your data accurate. The challenges in big data architecture, there are many, but one question that you need to ask yourself before you begin is, how fast do you need the insights? Can you wait a couple of minutes, a couple of hours, days? Or it has to be very fast, like sub-seconds and so on and so forth. Another question is, how complex are your compute jobs? Are you doing some heavy-duty joins? I have an example for theta join. Most people know join as select A star from a TATB, where TA index equals TAB index. What happens if you change the equal signs to less than? That's a mind-blowing query for the database. So in terms of velocity, different sizings of velocity will define your solution. I mean, under 1,000 events per second, it's usually not a problem nowadays. Over 1 billion events per second, you're talking a different ballgame, like, say, giants like LinkedIn, Google, and so on. Volume, 1 terabyte a day. It's a no-brainer in today's technologies. Everything above that, it really, really depends. Over a petabyte a day, I don't know a lot of use cases that generate a petabyte a day, but again, it also depends what you're trying to do. Velocity we discussed. Sorry about that. There's a lot of challenges. We're not going to go over them, but I just marked them because some use cases require answers for these questions. What are your performance targets or cost targets? Security restrictions is usually an issue. What technology to use, data center, cloud, latency, throughput, concurrency, access pattern is a huge problem in our company, for example. Are you using managed services in the cloud or just do it yourself over IaaS? In terms of rule of thumbs for architecture, you might want to decouple your architecture. So if something goes wrong in your big data architecture and it does not compute anymore, just replace the part which is not functioning well with something more performing without breaking the entire pipeline. As a rule of thumb, in a data center, you don't want to use over 3 technologies for your pipeline. But in the cloud, since everything is clickable, click, you have a technology, click technology, 7 is your maximum limit as a rule of thumb again. The reason why it's not recommended to use more, it's mainly because maintenance and complexity versus simplicity and so on and so forth. And don't forget training time. Taking a whole department or a whole organization and teaching them how to use these 7 technologies is a pain in the behind. So take that into account because that was a major problem for us in Aurora. How to get started? Well, by the way, this is like the 5th iteration of this lecture. I started that 2 years ago. And I realized that after the first session, I mean, I was talking for like 90 minutes. And then this lady raised her hand and asked a question. She said, I have a small question. I said, okay, I'm done, but sure, we have time. She said, so how do you do a big data architecture? And then I just grabbed my head and said, I must have done something wrong, and apparently I did. The structure was all wrong. So now I start with this lecture. So this is the methodology I used, okay? And I'm going to talk about it throughout the lecture. So feel free to stop me and ask questions, okay? Do it with your head like this. Good, you're with me. Okay, so the first question you need to ask yourself is, what's the business use case? You can then translate that into volume, velocity, variety, and so on. Second thing you need to ask yourself, did you map all your data sources? Do you know exactly what you're about to handle? Where should we build the data platform is also a huge question per company because sometimes there's restrictions, sometimes there's some irrational fear from clouds, sometimes you have to use data center and that's it. Architecture, there's a lot of open issues there, for example, pay-as-you-go or fixed. Do it yourself, pass. Is it fast? Is it cheap? Is it simple? After doing this several times, building several architectures of big data, I realized that the most important part is the communication. Communicating what you're about to do and why is it important, because it's so complex, and you're going to force people to work differently and think differently about data. So you better be prepared for some sort of a resistance in the organization for what you're trying to achieve, because it's going to be a long process. It's not going to be 1 week and we have a big data platform. It's going to be months, especially if you don't have the data, and it's going to be an ongoing process. And the last question, the last part of the process, did you map all known challenges? There are technical challenges which are different from each use case, and we'll talk about them in our lecture. So the business use case in Walla was, the first one was analyzing browsing history. Walla was part of Basic group. Basic has internet has users, and their browsing history was the end game. We wanted to know what are their patterns in terms of browsing the net. First challenges was...
Question, does the ISP, Internet Service Provider, trace the people? Trace the content of the website?
I have no idea. I was a Walla employee. I have no idea what an ISP does.
Everything is traced.
No.
I'm saying that the capability as
So the question was, is the ISP tracking people? And there's things that an ISP vendor is regulated to do and not to do. So if it all comes down to user consent, what you agreed in the terms of and conditions, of what you allow the operator to do. For example, there's a major mobile operator that got sued because it played a little bit with the data in a manner it shouldn't have been doing in terms of user consent. So one of their major issues, naturally, was privacy. But you have to understand in that specific project, since the complexity was high, the underlying assumption was let the legal, business, and technical tracks work in parallel, not activating anything into production without a green light in the end. So we work in parallel. So we got the use case, and we started working under the assumption it will take some time. The second use case was location-based data. The velocity there was the challenge. Naturally, again, the privacy. The velocity was 4 gigabytes per second. I don't know a lot of storage system that can handle 4 gigabytes per second, so that was definitely a challenge. And then the scalability was an issue. The rate was expected to double every year. So I had to do something to handle that somehow. Analyzing the location-based event, the idea was to get events in streaming, and the challenge there was, in my mind, I had a streaming architecture which consisted of many people and Spark steering, and my mind just blew away from the fact I need to maintain a Spark cluster for that, or any Kafka Flume solution cluster for that. So what I had in mind was to minimize, I won't move my hands because apparently every time I move my hand there's a noise. The idea was to minimize DevOps work to minimum and not hold a bunch of people there for just maintenance of streaming cluster. So getting started. I want you to all pay attention to the markings on the upper right. There will be a V or an X. So it will tell you in a rough sense what I chose or didn't choose, because we're doing some sort of an overview along the way. So the product here is clear. It ingests the data, it analyzes data, and generates insight for marketing purposes. For example, smart segments for online marketing, some smart reports for marketers, and some audience analysis, again, for marketing. The customers or marketers, publishers, agencies who deal with marketing. So the first question in the process is where to build, the second, sorry. Where do we build a data platform? At the time we did a long process of evaluating all the cloud vendors mentioned here, which is GCP by Google, Azure by Microsoft, AWS by Amazon, and the data center, which is what Walla used at the time. The reason we chose AWS after about 6 months of evaluating each vendor in depth, because we did a lot, very thorough competitive analysis, and AWS seemed to have all the right features for us at the time. And we wanted to reduce the learning curve, which was already extensive for us, and some of the people already knew AWS. So it made sense in terms of technical reasons. And of course, there was some business aspects as well. There's always that. So we talked about my big data. We talked about my product. But let's talk in terms of architecture. So what really my product does behind the scene has one layer that does ingestion for online and offline data. It does transformation to take data and transform it. We'll talk about it in a second. It does some data modeling and data visualization or presentation, choose your poison. It handles PII and GDPR regulation, and naturally it handles performance costs, simplicity, and best practices. So let's start from the end. That's my architecture, okay? What you see here is all the jargon I mentioned in a second, and we'll talk about each layer in depth throughout the lecture. So every time you lose something in the process, just try to remember these 4 steps: ingestion, transformation, modeling, presentation, and we'll start here and go up, okay? So, first layer is ingestion. This layer is designed to do one thing and one thing only: ingest data. It's supposed to handle different velocities, different types of data, and it's completely decoupled, meaning it's unaware of the next layer, what it's going to do. It only keeps a convention of our input and output. I expect something to get in the following format, and I expect something to give in the following format. So what we did, again here in the lower layer, we created for several reasons, several solutions. For all the use cases in the data center, I created a Java client that does a generic ETL from the command line. The reason I did that and not use a conventional ETL solution, I will talk in a second. And I also use some AWS Plus services, which I'll mention again in a second. The batch considerations. The idea was that the technical details were that we need to ingest in some of the use cases in a batch manner about 30 gigabytes of compressed CSV, which is not a lot, but there were peaks because the browsing history could end up in 200 gigabytes an hour, which was a challenge for a traditional ETL client that I worked with. So I did some 1 week coding, generated an ETL that I can go into a data center, just plug in extract, transform, and load commands. I can get an ETL every type of CSV to S3. The idea was to take a simple operator, give him the ETL, simple documentation, go punch in the command line, get a legal constraints of remove this column, hash this column, filter some rows, and then you get started by 2 seconds, more or less. And there was some performance issues in the code that took in advance, considered the fact that you may slow down. I mean, there will be peak in data, and then I just keep the data there and then gradually send the data on when there's enough bandwidth. Why not, your own ETL client? Usually it's a bad move, but not in this case because of bugs, maintenance. And one thing you need to consider, it's a bad practice to analyze at edge. So unless there's a good reason like IoT or anything else that you're not allowed or there's a bandwidth considerations, don't analyze at the edge because you cannot go back in time. So the best practice is to send everything, if possible, to the cloud, to a cheap storage, and then apply your logic on top of that, and if something is wrong, go back, change it again. So why not streaming? It's less accurate in our perspective. We didn't want to lose events. It's a bit more expensive, and not to mention maintenance. So wherever you can apply batch. So check your use case, how much time, how much latency can you tolerate in this business use case. 1 second. And then choose streaming if you have to go really, really fast in terms of response, or batch if it's allowed. Yes, question.
So why do you use your own Java ETL client?
So the question is why I use my own Java client. I was afraid that traditional ETL, can you hear me well? The traditional ETL client won't handle the performance target I was given. And you have to understand the context. I was entering a data center not controlled by me, with limited access, limited connectivity, and it had to work in one go and solve any problem you can predict in advance, because you're not allowed to go in as much as you like. It's not a data center controlled by you, so you have to make some sort of assumptions in the code and assume there will be problems and handle them automatically. So again, it's not a good practice. I just chose this because I thought it will be better in terms of performance. In terms of security, you have to know, this surprised me very well when I did this research. S3 has a lot of security features. For example, you can encrypt the data, you can transmit the data via encrypted manner, SSL or VPN. You can do some hardening. For example, you can define an AWS user that only is allowed to write to S3, not to read, not to delete, not to LS, which is very nice when you think about ingestion use case. You give a data center an app and you give them a user and you say, you know what, you're only allowed to write, nothing else. You can't do anything else. Of course, there's SCL restriction, IP restriction, and so on. Upload. Apparently, the AWS CLI is so optimized, it can use parallelism on the network and send stuff in parallel. So it's very useful. You don't have to take care of anything in terms of network. You have to take care of one thing only, saturate your bandwidth. So it's usually not a consideration, to my knowledge, in an ETL client, but my client handled that to saturate the LAN. And again, I was limited in terms of bandwidth on a data center of a client. Here's a technology I did not use. Scoop, it's an open source project, also part of the AWS. Everything we're going to discuss here is part of AWS, except 1 or 2 projects. The reason I didn't choose this because it's highly unlikely an end user will give you access to its source database. He will usually prefer to do his own ETL and dump some files somewhere or send you for streaming. So it's an irrelevant technology for our use case. Flume and Kafka is not part of AWS, and the downside of that is do it yourself. It's not trivial to get started, and again, you maintain a cluster and you need people with specialized knowledge about these technologies, and believe me, I spent months on Flume and didn't get the performance target I needed, and it was too much pain to get started. Transfer option from anywhere basically to our cloud. Well, there's an option for Direct Connect, which is essentially a dedicated LAN from the data center to your cloud. Meaning someone worked really hard to take a simple Ethernet cable and connect the data center to your cloud, meaning the data does not go over public internet, which is an issue in terms of security. But here's the thing, I was considering the telephone use case, the telco carrier with streaming with the location data, and the rate was 4 gigabytes per second, so it's not really something you can do over direct connect. And for all other use cases, simply relied on S3 and data at rest and in motion, so everything was secured enough for our purposes. Questions, guys? Feel free. Yes? We're good? Good. So, some solution...
I have one question.
Please.
Today in AWS, there is many options. I'm looking probably to set in USA, East Coast, or set a server in Europe.
Yes.
Which one is better from your experience?
It's not about better, so let's talk about the question first for the video. You asked about the difference between choosing a region in the US and a region in Europe. So it's not about a matter of better, it's a matter of two things. One, cost. A server in the US and a server in EU have different costs. Second, it's a matter of performance. If your end audience is in Israel, so the latency between a user here and a server in Ireland, for instance, is 80 milliseconds, 80. And the latency between the user here and a server in the US is 150 milliseconds. So usually it's not a problem because of caching and CDN solutions, but it really depends on your application. End of the day, bottom line, not a huge issue. Not something I'd worry about, unless you have latency-sensitive applications, for example, finance. So, ingestion in AWS, you have several options. You have the Kinesis client library, you have the AWS Lambda, EMR, and third-party do-it-yourself like Spark Streaming, Storm, Flink, and stuff like that. I didn't choose any of that simply because it was too much complicated for what I was trying to achieve. Kinesis family is divided into three. One, Kinesis Stream, second, Kinesis Analytics, and Kinesis Firehose. Let's start with what I chose. No, I didn't choose, sorry. Stream and Analytics, I didn't need in-flight analytics. I didn't need to near real-time processing, and I didn't require high throughput. I chose Kinesis Firehose because it's a managed service compared to the streams, and I didn't need no in-flight analytics. It's a managed service, so I don't have to worry about it or anything. I just click, and there's a streaming cluster, and all I have to worry about that someone streams data there, and that's it. I never touched it anymore. Of course, there are costs, but believe me, it's worth the cost. Comparison from one of the differences between streams and Firehose is latency. Streams can handle sub-second processing latency, and Firehose has a minimum buffer of 60 seconds. Again, can you wait 60 seconds? If so, Firehose. And the thing is, zero administration is very important in big data. Believe me, you will have a lot of problems in your architecture. Yes, please.
Yeah, so what are you using on the sending side? You said, like you had a slide that mentioned that you did not use our Kinesis agent.
Yes.
On this Java slide, what are you using for sending data into the Firehose? What is the
Yes.
sending process and data?
So the question was what I was using to send data or events into the files, but you have to understand the context. The context is streaming. Streaming is usually done by applications. For example, your mobile apps. You do something, an event is generated, the application sends the event through some authentication authorization to Firehose. Firehose takes the event, waits for 60 seconds, and then takes all the events
So you were sending directly from the mobile application?
Yes.
Or
From the entire group's mobile apps. There were quite a few.
I mean, like the actual sending code, was it on the mobile application?
Yes.
Or?
On the mobile app, there was a SDK that allows you to send code events. Okay, data transformation. This layer in the architecture, second layer, is all about taking data from the ingested layer that lands in S3, the storage layer, and transforming, meaning what? Let's talk about the definition. One, you take a CSV, which is role-based, and you transform it into columnar. This is quite useful in terms of cost, compression, performance, in some big data analytics use cases. Another thing you want to do in this layer is fix bugs in your data, if they exist. Sometimes there is, and you want to convert the type from CSV, for example, to Pocket, which is a binary file format from the Hadoop ecosystems. There are many. There are Pocket, Aurora, Orc, and then some more, but these are the most popular. We chose Pocket simply because it's columnar and it connects well with the rest of the ecosystem we are discussing in this lecture. So I use the EMR in the transformation layer. For this, EMR in AWS is this huge logo, but in fact, when you try to install an advanced option of EMR, you get a huge list of open source projects. This is a minor list, but the most dominant apps are Hive, Spark, Q, Presto. We'll discuss them in a second. One of the downsides of, let's talk about architecture for 1 second. It's a standard Hadoop distribution. It has a master node, core nodes, and task nodes, where the core nodes are compute and data disks, and the task nodes are only compute. There's no disks, so you can, if you're missing compute, just add task nodes and use them and save some money. One of the downsides of EMR in AWS, you don't have a standby master node like normal Hadoop distribution. But one of the best things, it's designed to be transient cluster. That means the cluster goes up and down every day. You don't keep it 24/7 alive, you reduce costs and you get the same impact. But you need to think differently. One of the lessons learned using EMR, this is quite important, but it's only a taste. There's a good article I wrote about it, about cost reduction and so on and so forth. Usually a bigger instance is good architecture. Instead of taking 1,000 nodes, which are small, take 100 nodes, which are 10 times stronger. You will benefit much more in terms of performance and cost eventually. If you're using Spark or Hive, try not always to use this. Sometimes MapReduce is better. This is for Avi. He asked me that question. But you really need to test. Network optimized instances really help you in terms of getting the data from S3. I didn't have a good experience with resize cluster, but some people say it works well for them. There's a bootstrapping option to automate your cluster when it goes up every morning or every night, depends. And one key thing to remember, use Glue Hive metastores. This allows you to keep the metadata of all your tables outside, so if the cluster goes down in the night, when you go up, you have all the create schema already ready for you, so you don't have to recreate everything. So EMR is very complicated because it matches a lot of use cases, so I'll break it down to several use cases. The most dominant ones are when you want to use Hive, Spark, and Presto. It's really good for transformation modeling, batch, Machine learning a bit less nowadays, but it's also doable. In terms of architecture, you can see here that you have the storage in one side and the compute is decoupled. This is what I want you to remember, and the metastore, okay, which is the metadata again. I chose Hive and Spark SQL. Specifically for the transformation layer, I choose Hive. Why? Because it has all the necessary flexibility you need in order to use SQL to transform raw data into columnar data. Okay, for example, take a CSV, convert it into Parquet, and remove some columns and do a regex on a specific column, and process some JSON with some nested schema, which you need to explode the rows and do some massive stuff, which would blow your mind. And there's another two key elements that were useful in Hive. One is dynamic partitioning and insert override. I will not go into that very much, but I will say this will simplify your ETL jobs in an order of magnitude, so take that into account when you generate some ETL jobs. Presto. The reason Presto is a SQL database over Hadoop, I didn't choose this because I was afraid I will end up with a large join in memory and I will eventually crash, because the join is done in memory, where Spark and Hive save the intermediate results to this. So if you fall, you can continue from the point you failed. There's no insert override. There's no dynamic partitioning, which bothered me a lot. I did some article about this with some features, but at the end of the day, I want to stress out, I didn't choose it for a specific use case reason. Doesn't mean it's not a good database. Pig, another distributed shell scripting. I didn't choose it because SQL was enough for me. I didn't need to do some scripting. Hue was a was part of EMR distribution. Nobody talks about it, but it's a really convenient tool to write SQL. It's web, so you can protect it really well, and all the data is on the web, so nothing is downloaded to your desktop. There's no traffic between your desktop to the server, so it's quite nice. And here's the kicker. It's installed for free automatically out of the box. All you have to do is check the box, I want you, when I install it in EMR. Orchestration. Orchestration is all about taking your ETL jobs and telling this job to run when and where. There are many orchestration solutions, but here's the kicker. Uzi comes out of the box inside of EMR. Nobody talks about it, but it's a good solution. It has some web, API, and command line options, so you can write code, you can send API requests, and you can see all your ETL jobs. So in the end of the day, this is the technology stack I choose for transformation. Hive, which runs on top of Yarn, and HDFS, which is the resource management and the storage. You can see the cursor, right? Tez, which was their engine to run the SQL queries, and Hue and Uzi for the orchestration and some SQL queries. Next layer, data modeling. This is the most heavy layer in the architecture. It's all about taking your data and modeling it, meaning joins, aggregation, some nightly jobs, and machine learning, and whatever you need in your use case. Let's start with the end again. I use SageMaker, which is a managed service, Spark SQL, Apache Zeppelin, R, Drift, Shiro, and Lively. Let's talk about Spark. Spark has many flavors and many options. When you say Spark, it's like saying a whole ecosystem of solutions. In general, there's Spark Core, which is this layer, and some APIs on top of it. For example, graphics, mlib, Spark Streaming, Spark SQL, okay, and some other supporting technologies like Yarn, or Zookeeper and so on. Spark streaming. I didn't choose it because of the DIY we discussed, do it yourself. It was too complicated for what we needed, and I didn't need near real-time latency. Spark ML, too much code for our taste, and doesn't connect well with the rest of the ecosystem for us. Spark flavors. We chose Spark with Yarn, which is, there are three options. Yarn comes out of the box in EMR, and all the tuning and performance is supported by AWS. It kind of makes your life easier when you want to tune jobs. The downside, compute intensive. Performance gain is not guaranteed. And again, streaming is actually a batch with a very small window. But again, if your use case requires streaming, do streaming. We chose Spark SQL. Sorry. Spark SQL, why? Because we didn't want to write code. We were very good at SQL. It's 10 times faster than Hive in some use cases. It works well with Zeppelin, which is another GUI for writing ETL jobs, do some analytics, some research, ad hoc. And that's it, basically. Apache Zeppelin, as I discussed, it's a notebook, it's a web solution, again, open source, again, part of EMR. You just click a V and everything works out of the box. It connects to all your databases in the AWS ecosystem. And here's something they don't talk about it very much in the documentation. The underlying infrastructure also installs for you Shiro, which helps you manage users, which is very nice, groups, user policies, read, write, and so on. And Lively, which essentially lets you decouple Zeppelin and your Spark cluster. Because all the documentation usually speak about installing Zeppelin on top of your Spark cluster, but Spark is compute intensive, so it really needs those resources to run on Spark. So what you should be doing is putting Zeppelin aside, and then use Lively as an API in the middle, and you just call the Spark cluster via Lively. It's detailed in, I think, lecture number 3 in this session. This lecture has 4 parts. Spark R, our data scientists were using R, and they needed to distribute their ML on a Spark cluster, and the challenge was how to connect R to your Spark cluster, because again, all the documentation talks about R installed on the same cluster as Spark. Again, the solution here was Lively. You put an API and you tell R, listen, use method of connection Lively, and here's the URL of the master node of my Spark cluster. Very useful. Redshift. Redshift is an all-up database managed service by AWS, a huge service, very old, like 12 years, something like that. It's designed to do petascale analytics. It's really good at what it's doing. It's one of the top 5 all-up solutions. It's completely ACID, fully SQL, fully managed, MPP, good for data warehouse and complex joins, really good solution. But we didn't choose it. Why? Because this is a cluster that works 24/7. Cloud native applications, cloud native architecture usually imply a practice that is called transient cluster, meaning you go up in the middle of the night, you run your jobs, and you go down and you don't pay nothing until the next night. Again, that depends on your use case. If you need a cluster which is 24/7 alive, that's one thing. But if you don't, and you only need a cluster that lives from 9 to 5, there's Redshift Spectrum, which lets you essentially do the following. You generate a cluster that goes up at 9 a.m. when people come to work, and you turn it off when everybody go home, 6 o'clock, for example. Let's say 5 o'clock, let's be optimistic. Here's the kicker, where's the data? The data is kept externally outside of the cluster on the storage layer, on S3. And all you have to do is create external table and reference the location to S3. Is that clear? Yes, no? Okay. I'm a cluster. I want all my data close to my CPU. Why? Because the CPU needs to be close to the data in order to hit the performance target over there and provide a good query experience. Meaning when Avi types a join query, the compute accesses the local storage, says, give me all your data, I want to do a quick join for Avi. Yay, here's the result, Avi, okay? But in terms of cloud, it says the following. We decouple the storage and the compute. Let's take my head, put it over here. Here's the compute. And we put the data over here, very far away. And we use network. And we tell the compute, listen, you don't have anything local. You have to access the data all the way over here. What's the penalty? Time. You wait for the data to go all the way back and forth. Okay? Which is good and bad. Why is it good? Because you can maintain a scenario where you can kill the cluster and you don't lose the data. Why is it bad? Because for a really heavy join graph, you go all the way, bring the data to the cluster, do your compute, give Avi the result, and then throw away the data. Okay? So it's good in one use case. What is that? Aggregations. You have a cluster with minimal compute. You go to Redshift Spectrum, and you tell them, listen, my data is over there. It's 1 petabyte. I need an aggregation. Spectrum borrows some compute close to the data, runs the aggregation, and gives the answer to Avi. You understand the difference? You're not utilizing the compute of the cluster, you're utilizing some additional resources in the back. So it's good if you have a exabyte and you need to run an aggregation. That would be very cheap and very fast. EMR versus Redshift. We didn't choose Redshift, we chose EMR. Why? Because our data scientists needed access to all our data every time they were working, and we used the same cluster for nightly jobs. There are many use cases to prefer this solution or another. You really need to discuss it. But as a rule of thumb, when you need some flexibility, go over EMR. When you need some traditional data warehouse, go for Redshift. There's some other issues like the amount of concurrency, petascale, complex joins. So there's a good article about that. We can discuss it in detail if you like later. SageMaker. This is the coolest solution AWS has launched in the last 2 years. It's an entire pipeline designed to do one thing, machine learning. Machine learning from the minute you take the data, clean it a little bit, transform it a little bit, select your machine learning run, do some training, do some validation, then deploy it to production. It's very useful because everything connects quite well. You fetch the data, you clean it, you train your model, you spend a lot of time, go back and forth, and then you do some deployment. It covers the entire ecosystem in one platform as a service. Very useful, or of course Jupyter-based. Everything is kept on your S3, everything connects to your databases, so it's really easy to create and get started on machine learning. I use that to create a simple machine learning that predicts whether a cookie ID is cookies if the anonymous cookie is indeed a female or male. That was important for commercials on online marketing. In this layer of Glue, layer of modeling, we use AWS Glue. Let's talk about that. We mentioned that before. Glue is shared meta store. Let's say we create a transient cluster. Remember an EMR cluster that goes up in the night and does all the ETL jobs and dies. So when the next day, when you launch a cluster, you want to have all your tables available, not to recreate them because the cluster is new. So this is why you have Glue. It's a managed service, again, that lets you keep all the metadata, meaning all your table, all your creates in one place that never dies when your EMR cluster dies. And another thing, it lets you do cross-cluster computation, meaning if you have one cluster and another cluster and another cluster, each of the cluster can use Glue to access the data in another cluster, which is very useful when you have a data lake. And another cool thing, it's a managed service that lets you to do some data transformation relatively simply. AWS RDS. We did use this for analytics. We use it as an operational DB. That's why the X. RDS is a managed service by AWS that is in fact your SQL server. Postgres, MySQL, MS SQL. The thing you need to know this is AWS has its own version of MySQL called Aurora. It's about 5 times faster than MySQL, and it's cheaper because you don't pay licensing fees, and it's decoupled in terms of architecture, so you can do some cool stuff like separate the write instance and the read instance, so your application only writes to the write instance. But there are many read clients, and you can scale out the read instances and can have one write instance and 17 read, which is quite useful in some use cases. For example, prepod, just give it the instance of the read only and you do no harm. Okay, so yeah. In terms of modeling, this is the architecture, this is the technologies we discussed. We're switching to the next layer, the presentation. The thing about the presentation, it's only used to present data via your application, dashboard, BI, or stuff like that. So you want to be using something like a managed service, like Athena, that it's serverless. That's essentially a database over S3. You can write SQL analytical queries on top of S3, and you don't maintain any servers, and you pay as you go, meaning for every query you run, all you have to worry about, how much data are you going to read? And the cost is quite simple. For every terabyte you read, you pay $5. So let's take Avi example. We like to make his life miserable because we're in the same team. Avi spends about $40 a month. That's the entire budget he uses for SQL queries on analytics on all of his tasks. That naturally uses from each user, it changes from each user. We got some heavy hitters. We call him Aviator. He's the guy who spends a lot of money in our company on pay-as-you-go databases. Okay, it's good for ad hoc queries. If you need some low-cost managed SQL analytical service, some known dashboards, you want to give some users the ability to analyze data via the dashboard, and you don't want a cluster that keeps falling and you need to worry about it. So it's relatively cost effective. When I first gave this lecture like 2 years ago, one of the guys raised his hand. He said, I have a cost reduction issue question about Athena. I said, okay, what's the question? I have a $4,000 monthly bill only on Athena. What can I do? So it kind of struck me because I didn't think anyone would use it so massively because it was at the time not so mature. So I wrote a good cost reduction article. If someone is interested, you can read about it. There are about 16 tips over there that can help. Visualize. Well, there's a solution by AWS called QuickSight. Essentially a cheap, affordable BI dashboard. Click 10 clicks and you have a simple dashboard over your data. Everything is connected, everything is seamless. Here's the downside, it's not Tableau. It's not so mature, it lacks complex functionality. So this is something good for internal use. I used it to monitor all my data, to see what comes in, what comes out, matrix, basic matrix, and so on and so forth. $10 a month.
Why not Power BI?
I didn't want something too complicated. I didn't know how to work with Power BI. It didn't connect well in terms of one click and I'm ready. I need to put a server, install license, convince the internal finance team to approve the purchase of a license, so on and so forth. This, I didn't have to ask anyone for permission. I'm admin, I press next, and I have a BI at reach. Again, I didn't use this for production, so it took me 20 minutes from the idea to the implementation. 20 minutes. It's that simple. Okay, some summary and takeaway messages. So we are ahead of time, so now is the time to really ask your hard questions. So this is the architecture. We have data ingestion. We talked about the Java client. We talked about Kinesis firehose for streaming. We talked about transformation to take the output of the ingestion layer that is saved on S3. It's completely decoupled, meaning ingestion is not aware of what happens next. Transformation is not aware of what happens in the ingestion layer. It only expects file in a specific format. It then operates over Hive and the rest of the ecosystem, runs some ETL jobs and transform that CSV into a colonel. Again, saved to S3. The data modeling layer, we use all this technology stack. We use Spark SQL to analyze the data science, data engineering. We use Apache Zeppelin for the ad hoc querying and some basic orchestration. R for the data scientist. Drift, I didn't mention it, but it's an open source solution that lets you connect via JDBC to Spark SQL. Again, not something mentioned in the documentation, but it's part of EMR service. So you just press start, and then you can connect from your desktop, from your IDE via JDBC, and that's like any other database. No need for code, by the way. One of the things you need to know that Spark SQL out of the box is not only SQL. You have to put some wrapper code, write some code, and open parentheses and write your query. So it's a bit non-trivial for beginners. But if you use the Drift projects, you can just send queries without code. So it simplifies everything for an analyst, BI, junior, data engineer, data scientist. We talked about Cheyo and Living. Don't need to go about this anymore. Athena. If there's anything I want you to remember from this technology stack in AWS, Athena. Start with that. Originally, before the architecture, I didn't know what to do, but I needed something to give fast for the data science team. So I started with Athena. I kept all the data here after the ingestion in S3, gave them access to S3, and that's it. They had a data warehouse for pool people. okay? And it worked. It was suffice for about 3-4 months. Why? They didn't know the data. They didn't know exactly what needs to be done, what are the data sources. So for basic aggregations, for basic ad hoc querying, this is the right tool for you. Once you need the complex, heavy-duty jobs, this is the layer for you. So, lesson learned. Decouple, decouple, decouple. If you keep your architecture decoupled, if something goes wrong, you change it. We changed the architecture technology stack several times. What you see here is the end result of a year and a half worth of work. Productivity is also a huge issue because data science team and data engineering teams spend a lot of time, and they need to communicate in a work in an efficient manner. So if a data engineer creates something which the data science team takes it about a week to understand what to do and how to do, and then writes a job and then pass it to the data engineer to put it in production, and you spend 2 weeks only to put the job in production, you missed something in your architecture. So when we used Redshift, that was part of the problem, because in the modeling layer, we had here Redshift. After Athena, we put some Redshift here. And then we realized that we couldn't use both Redshift and Hive because the syntax is different, the data types are different. There's no array support. There's no complex data structures here in Redshift. So whatever the data scientist wrote on Redshift, because he knows Redshift, did not compile on Hive. So we needed to invest a lot of time on converting and rewriting his job to put it in production, because this is a transit cluster. Redshift is not. Okay, so when you use Hive and you use Spark SQL and you use Athena, the syntax is the same. So it's a seamless migration. Minimize the amount of database used. Remember the rule of 7? Keep it this way. Okay, yes, I used a lot of technologies, but that's for the backend services. The end users didn't know more than Spark SQL, Athena, and Redshift. Okay? Streaming, again, depends on the use case, not always justified. So, something that surprised me about Spark SQL, it's sometimes faster than Redshift. You would expect that a traditional database like Redshift would be as fast as humanly possible, but again, there are some quizzes which it's not. Spark SQL is in memory, and Hive is on disk. So one would expect that Spark will always be faster. But again, that's not always the case. That really depends on the use case. Spark and learning curve, it's not trivial, but since it was SQL, the learning curve was minimized because there was no code. Usually when I do this lecture, one of these 6 questions repeat, and since you were nice to me and didn't ask any questions, I thought I could give you a slide about the most common questions. 1, can this be done on another cloud? 1, for you, Guy, I would really much appreciate it if you could say something about that later. From what I tested, you can do that, yes, for sure, on all other platforms. For example, on GCP, Google Cloud Platform, you have the Dataproc, which is their distribution of Hadoop. On Azure, you have HDI, Insight, and I believe Databricks. Correct me if I'm wrong, Databricks as well. Yes, good. And naturally, there's always solutions for vendor solutions like Hortonworks and Cloudera, which, by the way, they united into one company 2 months ago, I believe. And it was announced 3-4 months ago, so this merger should be nice. Cloudera is by far, I believe, the most dominant data center Hadoop distribution, which is paid. Hadoop originally is for free. You can download and install it. I did it once. Not something I want to repeat. Too much work, too much complicated. It's not their core business. If it's not your core business, don't do it. Redshift versus EMR, huge article about it. Athena versus Redshift. We covered it, but basically I want to reiterate it. Start with Athena. If it's not good enough, then switch to Redshift or any other platform you wish to examine. Cost reduction on Athena are very important. If you are using Athena for large scale, you have to consider cost. Pay as you go is nice when you start. It's not nice if someone, like an end user, spends too much time on the same queries and you're billed for each one. Surprisingly, one of the questions that kept iterating is how to export data from Google Analytics into AWS. Non-trivial, because it's exported automatically into BigQuery, which is the Redshift equivalent of GCP. Then you have to work really hard to export the data into AWS. And one thing you should consider, if you're using one of these Hadoop distributions, I believe they all support all of the cloud vendor storage layers. Meaning, this is hard, stay with me. I can create a Cloudera cluster which works on top of an external storage by AWS, by GCP, and essentially you can create a big data architecture which is completely decoupled from the cloud vendor. Too heavy. Okay, too heavy. So, main takeaway. From all the big data architectures I built in the past 7-8 years, I want you to remember one thing. A good big data architecture is all about three things: faster, cheaper, simpler. If you only have an architecture that answers 2 out of the 3, you did something wrong. Sometimes you don't have a choice, but when you do, take into account all the 3. Simplicity is all the learning curve and how much time it takes to learn the new technology and to switch data between teams and data access. Cost in the cloud is a very big, painful issue. Okay, for example, in the pay-as-you-go service, you can easily do a $10,000 mistake simply because you weren't cost-aware fast. Naturally, in big data, you don't want to wait the whole day for a query to finish, so you need to be very conscious about this. Call for action. As I said, this lecture is part 1 out of 4 lectures. This is the general lectures. The rest of the lectures go deeper and deeper in each of the 4 layers in the architecture. There are 2 meetups. Originally, I started in a meetup called AWS Big Data Demystified, named after this lecture. And then this year, I decided to go bigger and to remove the word AWS from the name. And this meetup, Big Data Demystified, I started last year. And then I met Guy, and with this joint venture. So this covers everything which is not AWS, for instance, GCP, data center solutions, NoSQL solutions. So stay tuned for some content. Naturally, everything is on YouTube channels and on our website. And all the links are here, my name, my phone, the website, the YouTube channels. So that's basically it. Now is the time to take pictures if you need. Everything will be available through Guy, the video, the lectures, and naturally you can contact me for any questions. I love what I do, so just talk to me. That's it.